Okay, everybody. So this is going to be the third and last video lecture that I have for this week. Hopefully they've not been too painful. Uh, this one's going to be over chapter 5 of the Navstar book, GPS absolute positioning determination, concepts, errors, and accuracies. These are just little summary lectures, so I'm putting a little something out there for you. Um, not to be substituted for reading. Please read this book as well as the gps.gov website. Get lost in this thing. Very fascinating. Lots of information. Like the other two chapters, I'm going to have a couple questions related to this one. That'll be part of the homework. I'm going to go ahead and start out with those, throw those out here. Um, One of the questions will be, which GPS error source do you think is most dangerous for a land surveyor and why? Thinking of things like multipath, atmospheric conditions, bad satellite geometry. Um, and imagine looking at a DOP chart. Everything looks great in the morning and terrible in the afternoon. How do you explain to a client why you're scheduling their work at weird times? I might reword some of these or come up with something a touch different. We'll visit that later. So as far as chapter 5, just kind of hitting some key points, brief summary of it again. Um, Show how individual GPS error sources combine into a total position uncertainty and how to manage them so the United States Army Corps of Engineers surveys meet the FGCS accuracy requirements. So, some key points looking at the error sources breakdown. We have things like satellite and ephemeris and clock errors, ionospheric and tropospheric delay. We'll also call those atmospheric conditions, and multipath and receiver noise. Antenna centering and monument instability. Together, they form the user equivalent range error, also known as and called the UERE. I'm going to try like heck to remember that. I just, military and all their acronyms. The user equivalent range error. So kind of looking at this a little further here, they look at the geometry in the DOP, the DOP, which stands for delusion of precision. The satellite configurations are summarized by the DOP. You have a GDOP, PDOP, HDOP, VDOP. A little bit further down the lecture here, I will go over what each one of those are in a brief description. If you have the same UERE and poor DOP, will equal a poor coordinate accuracy. A good DOP will equal a better accuracy. Pre-planning with predicted DOPs is a core part of survey design. This will be something else we'll get into. There's another website that is free to access regardless of what GNSS systems you use. You can use as a pre-planning software to kind of look to see what kind of conditions you'll be up against for a time. Again, these are planned. Some other things we look at is the differential technique and error reduction. Differential GPS and carrier phase methods cancel many common bias. Longer sessions, dual frequency receivers, and good network design further reduce residual error. Um, let's see, relating errors to accuracy orders. The UERE and the DOP are connected with expected horizontal and vertical accuracies. This is how you justify that a given method, occupation time, can meet first, second, or third order standards. Some quality control and validation concepts. Use redundancy, extra baselines or loops, closure checks, and least squares adjustments. I say this in a lot of other classes. I say it a lot, beating a dead horse here. One of my favorite sayings is for surveyors that redundancy builds confidence. Check, check, recheck, and then check again. Compared to achieved accuracies with specified FGCS order, document internal and external accuracy. So talking about geometry and DOP, uh, they're the bridge between measurement noise and positional accuracy. So what exactly is this delusion of precision, this DOP? GPS measures ranges to satellites. So each range has some error, which is the UERE, and how those range errors turn into positional error depend on satellite geometry. Good geometry, the errors cancel and average well, small positional error. Bad geometry, errors that are reinforced in some directions will cause larger positional errors. The DOP is a dimensionless scaling factor that tells you how much geometry will inflate the basic range error. Let's get into types of DOP. So I remember back, surveying using the GPS. Sometimes the data collector would start telling me poor PDOP. I'm like, oh, I feel bad for PDOP. Who's PDOP? What is that? PDOP is positional delusion of precision, 3D position, your X, Y, and Z, or lat, long, and height. There's a GDOP, which looks at geometric delusion of precision. That looks at the position plus clock. So it's kind of like a 4D-ish, if you will. HDOP is your horizontal. That's planimetric, looking at your latitude, longitudes. The VDOP is your vertical, which is looking at the heights only. And there's a TDOP, which is a time, looks at the receiver clock. For most of the survey work that you do, you're going to want to watch the PDOP, HDOP, and VDOP. There are factors when you're specifically looking at like the planning, you can see this. Um, Anything that's a factor less than 2 is considered good or excellent. Anything between 2 and 4 is good, 4 and 6 marginal, and above 6 is poor. So what does good geometry look like? This is very important for us. Good geometry kind of is underlying everywhere in surveying when we design our control networks and things like that. So good geometry with satellites, that looks like that's evenly spread around the horizon, has good azimuth distribution. So they're all around us. They also have a mix of high and moderate elevations. So not all of them are straight overhead. So looking at the horizon as 0, we typically have an elevation mask of like 10 to 15 degrees. So anything within that angle from the horizon, we exclude satellites that might fall into that. But anything from 15 degrees overhead back down to 15 degrees or 10 degrees, whatever, is also a good mix of high and moderate elevations. Different azimuths in opposite directions. So are they in the northern sky, southern sky, eastern, western sky? They're not all clustered maybe in the southern portion of the sky. Oh, darn it, I did it again. Let's see. It's right about here. Stop. Technology is wonderful. We'll start dancing around and make that thing move all over the place. So bad geometry examples would be satellites that are bunched in one sector of the sky. So if they're all clustered directly overhead, directly in front of you in the northern, southern, eastern, western skies, whatnot. Or they're all roughly one-dimensional distributions. So if you have maybe multiple satellites that are all kind of in line with each other, shooting the same signal, you're receiving the same signal, and multiple are in the same line, that would be bad. So when you are working in like a downtown environment, urban canyon, around tree lines, canyon walls, things like that, that kills geometry. That really severely limits to maybe what is exactly overhead. You may have enough satellites, however, you can still have a bad illusion of precision. Um, so how geometry and DOP feeds into planning, some things you're going to want to look at is predicting the DOP for your site and time using some planning software. I'll pull up a website and show you one that is by Trimble. I should actually add a link of that to the module as well. Schedule sessions when your PDOP and HDOP are low and stable. Avoid observation windows with high PDOP spikes. Document that the survey was done under acceptable DOP conditions as part of your quality control checks. In practice, pre-survey planning should include these steps. Choosing an observation window when your DOP stays below your project threshold. Extending session durations so you observe through different geometries, which helps average things out. And rejecting epochs in processing when DOP or satellite count is poor. The extending sessions during extending the session duration when you are out observing is very critical. There's been a lot of times I've done this personally out in the field. We come and set a monument. We observe it for whatever the boss wants us to. Come back, maybe we observe it in the morning, and we go do some more work, set some other control points, shoot them in, whatever. Come back in the afternoon, set them or observe it a second time to get a completely different satellite geometry. Ideally, you know, I've always heard best practice would be come back another day. I think we all know in this day and age with time is money and trying to be efficient, that's not always ideal. We can't always return to a job site for another day to observe. If you can, wait a minimum of a couple hours if possible and observe a second time. So those are some of the things from chapter 5. What I want to do here is show you a quick other website that has some planning involved in it. Again, looking at this GPS website, which I have a link to, so much information. There's some more information. I just noticed this resources for teachers. There's a bunch of things. Maybe I'll print that poster, put up on our classroom wall for all of you to enjoy that aren't here. Never mind. I might actually look into this and utilize a little bit more of this information in our class moving forward. So here is a Trimble website that is for GNSS planning. Now I am saying GNSS specifically because this does include GPS, Russia, Europe, China, and Japan. As we can see here, we jumping ahead of myself here. So if you look over here at the map, I have a latitude, longitude set. That is here at school, Cincinnati State. Starting with today's date, going from 8 o'clock, using the correct time zone, and saying a period of 12 hours. We'll get into this a little bit later, but the time zone thing is kind of tricky over here in the eastern United States. depending if we are 4 hours or 5 hours behind the Greenwich Meridian time, depends on if we're in daylight savings time or not. So that can change. We'll talk about that a little bit more in the following weeks, or at least I'll bring it up to your attention. So what we have here is the settings. I set my position. I set the time where I want to look at the satellites and all the various information, the DOP, the positions, to get an idea for geometry. I'm also choosing, I'm going to say, go ahead and show me everybody's constellation. I can select just GPS, or I can take out other ones if I so choose. Up at the top, here's a satellite library. If I click on this, I can see here I'm looking at all the GPS constellations. They're all good, they're healthy. I believe if you wanted to, you could unselect if you, for some reason, have information like I don't want to use this one specific satellite or not. You can choose to do so. However, you can see they're all good and healthy. You can toggle through and see if GLONASS has anything going on, Galileo, the China, and Japan. I could be wrong on this, but I believe Japan's satellites are in an orbit that basically stay over Japan. They're not completely circumnavigating the globe. I believe they're staying right over their country specifically, at least as of right now. Next, we'll come over here and look at the charts. This gets, I guess, a little confusing, or it's just a ton of information. Again, we got everything selected. Maybe we'll just go ahead and look at just the GPS specifically. We'll turn everybody else off. We'll just look at the GPS right now. The elevation here has to do with the degrees from the horizon. So your horizon being 0, going up. This is, you can see, you do not want to use satellites that are very close to your elevation mask. You want to be careful with them, I should say. This signal is coming through the atmosphere at a greater, steeper angle to you. When it goes through the ionosphere, troposphere, think of physics and light going through different mediums, how it bends and reflects. Kind of the same thing here, where you want to kind of maybe pay attention, be a little more careful of satellites that are going to be close to that cutoff mask or close to the horizon. From our specific location here, we can see the number of satellites we have at any given time. We're looking good. We definitely have more than 4. Here we can look at the difference in the DOP values. So we can see they're different color coded. We have the geometric, time, position, horizontal, and vertical. So the GDOP, TDOP, PDOP, HDOP, and VDOP. Again, this is kind of a unitless or factor. Anything below 2 is supposed to be exceptional. Anything between 2 and 4 should be good. 4 to 6 is questionable. Anything above that, you definitely want to ignore. And also looking at this, keep in mind we're looking at military time. So once we get past noon, we start getting 1, 2, 3. We're getting into 15, 16, 17 military time. So it looks like you are not going to want to be out around 1830, 1840. Looks like everything's spiking. That would be what, 640? We also can see our visibility. So given the elevation mask, when satellites are going to be traveling overhead, when we will see them. And the ionospheric index, I would need to read up a little bit more on this myself. So here's the general sky plot. You are at the center. These are how the satellites actually look overhead. So like your G29 up there in the top right, that might be a little questionable because you're getting close to that elevation mask, which is shown here by the light blue line. The faint circle all the way around, that would be 0. That's your horizon. That looks like pretty good geometry right there. One more thing we have here, we can look at the world view. This kind of also puts another perspective on how everything's looking and where it's at. So that G29 at 6 o'clock, well, currently it's kind of between France and Spain, right at the border right there right now. So I'm sure by 6 o'clock that's going to be further south of where its current position. But here's where we can see how those are actually going around the Earth. So this pre-planning, is it really necessary quite right now? Oh, wait a minute. Let's see. Look at that. We can put it in motion and see how those satellites are moving. That's amazing. So G29 was actually coming from the south, going north. Wow. I really just kind of wanted to show you this this website just to give you a general idea of some pre-planning type options we have. Again, we'll have some questions over chapters 2, 3, and 5 that will be part of homework. Um, please read the book and feel free to peruse through this website. It looks pretty informative, pretty good. Don't get too lost in the rabbit hole. All right, we will talk to you next week. If you have any questions, please feel free to reach out. Send me an email. If you want to schedule a phone call or a Zoom meeting sometime, I'm always available. Well, I'm available during my office hours. If those don't work for you, shoot me an email. We'll see if we can schedule another time that works best. And look forward to talking to you. And I'll see you next week.